Okay. Hello, everybody. We're going to, what are we doing? Keep going with chapter 6, section 6.1. So last time I was stumbling through because I was having to read notes from my phone, but now I've got my notes here. So this should go a lot smoother. Okay. So we left off. We were finding, so the 6.1 continued. The whole goal was we were finding P of xy, some point given some t, which is an arc length and also an angle, right? So we saw, just to kind of reiterate all this, so t is specifically an arc length along the unit circle. So if I draw a unit circle centered at the origin, right, with radius 1, here it is, and I didn't draw my picture good, so there's that and that. So the point 1, 0, the point 0, 1, etc. And t, t was that arc length along the unit circle and subtended by also an angle t, right? Because on the unit circle, arc length is exactly equal to the measure of the angle that's subtended by that arc, it measured in radians. Okay, so we were finding, given some t, what is the coordinate point that t lands at? That's what we were doing last time, and specifically we were doing an example where I was giving you t values that landed you on some of the axes, right? So I believe I left you with some. I'm just going to do, I think I left you with f, g, and h. I'm going to do h. So this is example 1. No, it's not example 1. It's example 3 from last time. Part h is what I'm going to do, which is negative pi on 2. Okay, we already talked about that. Okay, good. So, oh, and this is t. This is, t equals negative pi on 2. And I want to find the corresponding coordinate point. And by the way, the kind of the big idea was that for a given, on the unit circle, for a given t angle, we can say that x is equal to cosine of t and y. So for the coordinate point, x, the x coordinate is cosine t, and the y coordinate is sine of t. Okay, so I gave you a t value that's starting at, they always start at 1, 0. Okay, and it's negative. It's going to negative pi on 2 for part h here. Negative pi on 2, which goes like that, this way. So that's t equals negative pi on 2. And I'm asking, what is that coordinate point? So you could just go straight to this, right? X equals cosine of negative pi on 2, and y equals sine of negative pi on 2. But, sorry, got distracted here. Okay. But we also just know that these axes points on the unit circle, they're 1, 0, 0, 1, negative 1, 0, and this one is 0, negative 1. And that's all we need to do there, right? That's all we need to do there. So P of xy is equal to, just by knowing that we're landing on that negative y-axis, is 0, negative 1. Okay. What about our other special angles and multiples of them? So I talked about 0, pi on 2, pi, 3 pi on 2, 2 pi. So what about the pi on 6, the pi on 4, and the pi on 3 angles. So just considering this first quadrant here, I'm looking at the, hang on one second. I feel like I'm going out of order. Did I get out of order? Let's see. No, that's okay. All right. Okay, so pi on 6 is going to be right here. Okay, so here's, let me draw my circle. That's supposed to be a circle. Still on the unit circle, 1, 0, and this point is 0, 1. Okay, here's my pi on 6 angle, and then my pi on 4 angle would be right down the middle, and then of course my pi on 3 angle. So what about these? What are the coordinate points? So what are p of x, y for each of these different angles here for the pi on 6, pi on 4, and pi on 3 angles? Well, we know that for t equals any angle, p of x, y should be, well, we can get it straight from sine and cosine, right? Should be cosine of pi on 6. That's going to be the x value, comma, sine of pi on 6. Sine of pi on 6. Okay, but we already know these, right? Or we should, right? Okay. We have the pi on 6 reference triangle. So how do we figure these out? Remember, you draw your little reference triangle with the pi on 6 angle. So here's pi on 6. If you can see that, that's pi on 6 in there if you can't see that. Okay, it's a right triangle. I know this side is 1, this side is square root of 3, and this side is 2. Just coming, we talked about the construction of this triangle, but really, right, we just kind of all came to terms with the fact that we need to memorize this reference triangle. If you recall, it came from an equilateral triangle, but I mean, honestly, like when I was going back to review for teaching this course, I didn't even remember where the triangles came from because I just committed them to memory and that was it. Right. Now, anyways, cosine of pi on 6 is supposed to be adjacent over hypotenuse, right? So in general, cosine is in a right triangle should be adjacent over hypotenuse. So we're getting the x coordinate as square root of 3 over 2. And sine of pi on 6 is opposite over hypotenuse, so I'm getting 1 over 2. Okay, so this is for t equals pi on 6. This is for t equals pi on 6. Okay, for t now, and I'm going to redraw this picture. Once we get all three of these, I'll redraw this picture and make it look a little better on a fresh sheet of paper. For t equals pi on 4, p of xy should be, again, the same thing, should be cosine of pi on 4, comma, sine of pi on 4. Okay. Okay. Okay, so this is going to be a 45, 45, 90 triangle, right? That's the pi on 4. That's the pi on 4 angle, pi on 4 in there. And we know that this should be square root of 2, square root of 2, and 2. So our coordinate points should be adjacent over hypotenuse, so square root of 2 over 2, and square root of 2 over 2, the same for sine, opposite over hypotenuse, opposite. And remember that I've taken this triangle and I've scaled it up. Because we were writing it as 1, 1 square root of 2, but I just multiplied everything by square root of 2, just kind of resting on the one that has the rationalized hypotenuse here, because the hypotenuse ends up in the denominator. So it's nice to have the hypotenuse already written as a rational number, so I don't need to worry about rationalizing my denominators over here. All right, last one is pi on 3. And since you're probably already there, I'll just kind of skip and say that the coordinate point is going to come from a very similar triangle, but it's oriented differently. So we're going to end up with the cosine of pi on 3 yielding 1/2, and the sine of pi on 3 being square root of 3 over 2. Okay. So all of this looking very familiar to chapter 5. Let's draw these angles in a nice picture, just the first quadrant, right? So you're probably noticing that I'm only considering these first quadrant angles for now. Of course, next thing we're going to be doing is, let's see, going beyond the first quadrant, but for now we will stick here. So here's my unit circle in the first quadrant, just looking at these nice acute angles. So the smallest angle, which just for your sake, I will color coordinate here. I got, for the pi on 6 in blue, I got this coordinate point. So here's pi on 6, which is roughly 30 degrees. That coordinate point I got as square root of 3 over 2, comma 1/2. This was t equal to pi on 6. Okay, then right down the middle, 45-degree angle, pi on 4. So t equals pi on 4. If you can't see that, this blue one is t equals pi on 6, the red one is t equals pi on 4. And of course, this one ended up being square root of 2 over 2 for both x and y. And then the pi on 3 angle is the 60-degree angle, the biggest common one that we have in that first quadrant, besides pi on 2, which is the 90-degree. So we have t equals pi on 3. And that was very similar to the pi on 6, except that the x and y were swapped. All right. Now, what about going beyond the first quadrant? For our special angles beyond the first quadrant. I might be going a little bit out of order with the book here, but this feels more natural. So what about the special angles outside the first quadrant? Okay. Okay, again, I'm kind of gonna give it away. I'm gonna kind of give away the big punchline here, but then we'll talk about more detailed analysis of like what's actually going on here. But so first of all, what are the special angles outside the first quadrant? I'll start with the smallest one. The pi on 6 is, you've got your pi on 6, 2 pi on 6 is just going to be, it's already pi on 3, right? 3 pi on 6 is just the pi on 2 thing. So the next actual pi on 6 angle I'd want to consider is the 5 pi on 6. And then 7 pi on 6. Stuff that does, I don't want to consider, these fractions that reduce to just be other nice ratios. So considering those that don't reduce to just be other common angles. So pi on 6, 5 pi on 6 would be 5 pi on 6 is going to be the one over here in the second quadrant. 7 pi on 6 is over here in the third quadrant, and 11 pi on 6 is over here in the fourth quadrant. Okay, then you've got the pi on 4s. You've got your 3 pi on 4, so first quadrant, second quadrant. Your third quadrant one will be 5 pi on 4. And then your fourth quadrant one will be, so there's going to be one of these, and I'm saying etc. because you can keep rotating around the circle, right? But this is just the first 4 quadrants, the first iteration of each one. First quadrant, second quadrant, third quadrant, fourth quadrant. And then the pi on 3s, you got your pi on 3, 2 pi on 3, 4 pi on 3, and 5 pi on 3. Had to think about it and make sure, yeah, and etc. Okay, here's the thing. All we need to know is we need to know 2 things, is the corresponding coordinate point in quadrant 1. So that means, you know, if I'm dealing with a pi on 6, then the corresponding coordinate point is this one I wrote in blue, square root of 3 over 2 comma 1/2. If I'm dealing with a pi on 4, then it's this coordinate point, etc. So I need to know that. So if I'm going to ask you find t equals 7 pi over 4, what's the coordinate point there? You need to know what is the corresponding coordinate point for your angle as it exists in quadrant 1, and what is the sign like plus minus, of the trig functions in the quadrant where the given t value lives. This is how we're going to deal with special angles outside the first quadrant. By the way, what are the signs of the trig functions, the trig functions in the other quadrants? Well, they're both, so remember it goes cosine, remember these coordinate points are cosine t, sine t. So they're both positive in quadrant 1. Cosine is negative in quadrant 2 and sine is positive in quadrant 2. They're both negative in quadrant 3. Cosine is positive and sine is negative in quadrant 4. Okay, so as an example, all right, let's find p of xy for t equals 7 pi over 6. First thing I'm going to note is that in the first quadrant, t equals pi on 6, p of xy is square root of 3 over 2 comma 1/2. That's straight from that's the info I just gave you a minute ago. Okay. Also, note that, so for my actual angle I'm given, or actual number here, t equals 7 pi on 6, note that is in quadrant. Well, where is 7 pi on 6? You know, think about that. That's, you know, 7 pi on 6 is a full pi plus a little pi on 6, right? So if you need a drawing of it, it would be like there's pi, that would be 6 pi on 6, right? And then a little extra pi on 6, so it's there. This would be t. All the way down here. So it's in quadrant 3, where both coordinate points should be negative. Both coordinate points must be negative. So what's the coordinate point? P of xy is just going to be negative square root of 3 over 2, comma, negative 1/2. That's it. You just have to know what is the point for the corresponding t value that you're given. And also, what's the sign in that quadrant? Okay. Okay, let's analyze this process in a little bit more detail, though, because that's kind of just, I'm kind of waving my hands a little bit. It's kind of pushing a lot of details under the rug. So let's actually analyze this, and how would we go about this? All right. Okay, so here comes a definition similar. So here comes a definition similar to reference angle, which is the way we got out of the first quadrant in chapter 5. We had a definition called reference angle. We're going to have a new definition called reference number. Instead of angle theta, we've got a number t, but really t is an angle, so I could still technically call this a reference angle, but I'll call it a reference number. That's what the book calls it. So the reference number t bar for t is it's very similar. It's really the same thing. The shortest distance. Remember, I told you chapter 5 is going to be, chapter 6 is kind of chapter 5 repeated, just in a different setting. Is the shortest distance along the unit circle between the terminal point of t, and the x-axis. All right, so what does that mean? My t is outside of the first quadrant, right? Well, it doesn't have to be, but as an example, I'll draw t outside of the first quadrant, maybe all the way over here. So here's t. T bar, the reference number for t, is the shortest distance still along the unit circle, so somewhere along this unit circle, between the terminal point of t, which is right here, and the x-axis. What's the fastest way to stick along the unit circle and get from this point to get back to the x-axis? Well, I can either go this way or I can go this way, and this way is definitely shorter. So that's t bar. So it's just like reference angles. If your angle is positive and you end up in the second quadrant, then your reference number should complete that arc. If it ends up in the third quadrant, remember how there were different rules for each quadrant, and we said, like, really not best to just memorize them, just kind of understand it instead of trying to memorize. So if this is t all the way in the third quadrant, I'm supposed to go from along the unit circle, the terminal point of t, back to the x-axis along the unit circle, so it has to follow the arc. I can either go like this to get back to the x-axis, or I can just go straight back, and of course that's going to be what I want in this case. So sometimes it falls back on itself, and sometimes it just completes the arc. In the first quadrant, if t is in the first quadrant, they would just be the same angle, right? Or same number. Okay. This is going to be like the more technical way of getting outside of the first quadrant. So example 5. Find the reference number for each t. Okay, part A says t is equal to 5 pi on 6. Part B is t is equal to 7 pi on 4. C is t is equal to negative 2 pi on 3. And D is t is equal to 5.80. 5.80. So that's a weird one, but that's okay. We'll deal with it. All right, so part A. T is equal to 5 pi on 6. I'm going to quickly draw that. 5 pi on 6 should be just above, it's not quite pi, right? 6 pi on 6 would be a whole pi. So it's like right there. Oops, like more like that. That's T. So T bar is going to complete the angle. T bar there. So T bar for part A. Of course, if this is 5 pi on 6 and it's completing half of a revolution there, then that's going to be pi on 6 to complete that pi half revolution. All right, now part B. Okay, so I hope this is all making sense. Maybe you guys are bored because it's really just kind of the same thing as reference angle all over again. 7 pi on 4 is down over here in the fourth quadrant. Right there. Because I know that 8 pi on 4, right? 8 pi on 4 is a full 2 pi revolution, so I'm like a pi on 4 back from that. So now T bar is going to complete that revolution. That's the shortest distance from terminal point of T to the x-axis. So T bar is going to be just a pi on 4 there. That's a pi on 4. All right. C is going to be negative 2 pi on 3. So that's pi on 3 would put me here, and then another pi on 3 going the opposite direction this time, right? So going this way, there's T. So this is the T equals negative 2 pi on 3 angle. And I want to find my reference number. This one is going to complete the angle, T bar there, and it should always, remember, reference numbers and angles are always positive, so this one must complete a full revolution, right, sorry, not a full revolution, a half revolution, so T bar must be pi on 3. And now this weird one, this is measured in radians for the T equals 5.80. I know that that should be, since I know that 2 pi radians is like 6.28, just from knowing that pi is 3.14. So I know 5.8 should be somewhere, I don't really know, somewhere over here. So it's going around and going like that. That's T. So T bar I know should look like this, but how do I actually calculate it? How do I actually calculate that T bar there? Well, I just take a full revolution, which is 2 pi radians. So I'm going to do it in a different color so it stands out here. 2 pi radians minus this 5.8 will give me this little leftover piece. So I'm taking a full revolution and I'm subtracting this arc that I drew in black here, which is representing 5.8. I'm subtracting that. It's going to leave me with this little piece here. So this will be, if we round, we'll say approximately 0.48. Wait, is that right? 628 minus, yeah. Approximately 0.48. So when you're dealing with numbers that are not explicitly written as like fractional pi values, you know, it can get a little weird, but still just trust the geometry and you'd still, so the necessary thing to know is that a full revolution is 2 pi and a half revolution is pi, stuff like that. That's what got me to this answer. Okay, so that's finding reference numbers. Now, can we find so again, I'm just working through kind of like the long way of doing, the more technical way of doing example 4, because I pushed some details under the rug with example 4. So using reference numbers, find the terminal point, which is p of xy, for each value of t. Let's say t is equal to 7 pi on 6. So we already know this one, but what does this look like if we do it by reference numbers? So first we draw the angle. 7 pi on 6 is in the third quadrant down here. So that's t, 7 pi on 6. So I see that my reference number should be going from here to here. T bar is going to equal pi on 6, just from the geometry there. Pi on 6. Okay. Now I find the terminal point for this angle. So the terminal point for pi on 6, that p of xy is equal to square root of 3. So it's kind of really just the same thing happening again. Is the reference number thing really useful? Well, sometimes it is. It's just a different way of thinking about it. Maybe you like how I did example 4 better, where I did sweep some details under the rug. Maybe it makes more sense to you. But technically what we're doing when I say, back here where I say, where did I write it down? All we need to know is the quote unquote corresponding coordinate point in quadrant 1. That idea is really getting to, that's like me saying the reference number. Okay, that's all that's going on here. Okay, so once we do that, once we find the corresponding point for the reference number, which is pi on 6 here, so I've got that written down. Now I just think about the signs in the third quadrant where my actual t value is living, and by the way, they're both negative. So my actual p of xy for my given t value is negative square root of 3 over 2, comma negative 1 over 2. Part B, I'm going to skip around a little bit. Let's say t equals negative 2 pi over 3. So we've already found this reference number. We found it to be t bar equals pi on 3. So the corresponding terminal point at pi on 3 was 1/2 comma square root of 3 over 2 from my first quadrant, 1/2 comma square root of 3 over 2. So what else do I need to know? Well, I need to know where is this t value. This t value, which we drew, for example, whatever, 5, that t value, negative 2 pi on 3, was in the third quadrant. So this is in quadrant 3, where everything is negative again. So my p of xy for this, for the actual, value that I want, is negative 1/2 comma negative square root of 3 over 2. Okay, 1 second, let me get some more paper. Okay, let's do part C. Let's do that 5.8 one again. So we found or not do it again, but let's identify it a little bit more. 0.48 was the reference angle or reference number. How do we deal with this? Like, we don't know, like this is in the first quadrant, that's good. So we can figure out what the corresponding coordinate point is for this, for this, but we don't know like exactly what it is. It's not going to be like square root of 3/2 because it's not like a pi on 6 or pi on 3 or pi on 4, right? So how do we write it down? We say it's cosine of 0.48 and sine of, we just fall back on that definition of the coordinate point. It's cosine of t, sine of t. And I'm finding it for the reference value right now. So that's going to give me p of xy is equal to, and I didn't write it down, so give me 1 second. I got to calculate that. 0.48, and make sure I'm in radian mode for sure. Cosine gives me, I'm just going to round to 0.89, and then sine, 0.48 of sine is 0.46, yeah, 46. Okay, almost done. What do I do now? I note that t, back the original t, not t bar, but t was in quadrant 4, right? It wasn't in quadrant 4. Let's see, 5. Yes, so that's where x is positive and y is negative. So my actual coordinate point, it's going to be the same numbers, like same digits, but x is positive, 0.89, and y is negative. Okay. All right. Good. All right. Oh, I can leave that there for a second longer. All right, here's one last note and example for this section. To find terminal point for large values of t, so when I say large, I mean like bigger than a full bigger than 2 pi, bigger than a full revolution. Consider that extra revolutions, or rotations, you could say, do not have an effect, do not on the point, that coordinate point at which t lands. So if I have, for instance, t equals pi on 4 right here, t equals pi on 4, that coordinate point, xy, is going to be the same as if I had something that goes all the way around and then lands back on pi on 4 again right here, like t equals, what would that be? That would be 9 pi on 4. These coordinate points are the same. Okay, so how are we going to use that? Well, example 7, right? Yeah. This is just kind of an extra note about really large values for t that might be given in problems. Find the terminal point. So when I say terminal point, I'm asking for x, y coordinates. Find the terminal point of each t value. So same instructions, but bigger t values. T is equal to 29 pi over 6. Let's start with that one. Okay, here's what we're going to do. We're going to note that there are extra revolutions here. 29 pi. What does an extra revolution in terms of pi on 6 look like? It looks like 12 pi on 6, right? 2 pi. 2 pi is a full revolution on the unit circle. So 12 pi over 6 is going to be an extra revolution. So note that 29 pi over 6, and I'm going to come down here to write this because I'm going to need some room, is equal to 12 pi over 6 plus 12 pi over 6. That's 24 plus 5 pi over 6. These are extra revolutions, right? This is a whole extra revolution, and this is another whole extra revolution. This is all I need. So I can work with, when I draw my picture, t equals 5 pi on 6. That's not my reference number yet, right? Where is 5 pi on 6? So that's right here. So this is my t equal. I'm going to go back to writing the original one in black, and then I'll write the t bar here in red. So t bar here is going to be pi on 6. Pi on 6. Which has, so we've already considered this one several times. This has coordinate point, terminal point, square root of 3 over 2, comma 1/2. So for my t equals 5 pi on 6, which is what I'm dealing with, right? My original angle is 29 pi on 6, but I don't need to consider those extra 2 full revolutions. 5 pi on 6, well, I'm in quadrant 2, right? My t values, 5 pi on 6 is in quadrant 2, where x is negative and y is positive. So I'm getting negative square root of 3 over 2, comma 1/2. That would be the solution to this problem for 29 pi on 6. The point is, t equals 29 pi on 6 lands at the same spot as t equals 5 pi on 6. So we just work with this one. We find the reference number of this angle and do everything we did in example 6. Just taking away the extra revolutions. Okay, part B. (21 pi over 4). So I'm going to note that 21 pi over 4 is equal to, well, what does a full revolution look like in terms of pi's on 4? It's going to be 8 pi on 4. And there's going to be another one, 8 pi on 4. That's 16. And then what's the last one? 16. To get to 21 is going to be 5 pi on 4. So really the angle I want to consider is t equals 5 pi on 4. And then I'm going to kind of skip some steps and assume, since we've done enough of these, that you can come to the conclusion that the terminal point of the 5 pi on 4 angle, which by the way is in the third quadrant. Did I mess something up here? 3, 5. Yeah, third quadrant, where both values are negative. We're getting negative square root of 2 over 2 and negative square root of 2 over 2. All right, that concludes section 6.1. All right, 6.2 now, straight into it. 6.2. Trigonometric functions of real numbers. Just abbreviating trig functions of real numbers. All right. Okay. So let me just glance through my notes real quick. All right, I spent like the first half of this page just kind of reiterating everything that I just went over, so I will not redo that, will I? No. Let's just say let's just recall or note that for t on the unit circle, the terminal point is given this way. Okay. So what am I saying? That x is equal to cosine of t, right? And y is equal to sine of t. Okay. On the unit circle. So from this, we can define every other trig function. From this, or from these rather, we can define tangent of t, right? We can say, well, here, how about for the bigger picture here? This is coming from a right triangle with some angle t, some angle t here. This value, so some coordinate point up here, x comma y. The height of the point is y, the horizontal distance here is the x, and of course the radius is 1 because we're on the unit circle. Okay, so this is so y is equal to, or rather, sine of t is equal to opposite over hypotenuse, which is just going to be y over 1, so just y. Cosine of t is going to be equal to adjacent over hypotenuse, which is x over 1. Tangent of the angle t is going to be equal to opposite over adjacent, which is going to be y over x. Okay. So we're going to define all these trig functions with an input of t outputting either x or y's. What's next? Cosecant of t, which by the way is supposed to be the reciprocal of sine t, so we should see 1 over y. Let's see, what is it supposed to be? It's supposed to be hypotenuse over opposite. That's 1 over y. Good, so that checks out with it being the reciprocal of sine. And then secant of t is hypotenuse over adjacent, which is 1 over x, so the reciprocal of cosine. And then finally, we have cotangent of t is adjacent over opposite, the reciprocal of tangent, so we're getting x over y. Note that all of these four, unlike the sine and cosines, these will all have domain issues. When x or y are 0, right? So like tangent can't have x being 0, neither can secant. Cosecant can't have y being 0, and neither can cotangent. Okay. That's just a note for when we talk about their graphs later. We're going to see something happening for these things. Certain values of t are going to be not allowed. But more on that later. Okay, so where are we at now? What are we going to do now? Well, we're going to start evaluating the trig functions at different real number t values. So example 1. Example 1. Evaluate the 6 trig functions, so all 6, so sine, cosine, and then these 4, for t equals pi on 3, and then we'll also do t equals pi on 2. I've got a couple other ones listed, but I think I'll skip those just for the sake of time. Okay, so part A, solution in red. So Here's what we're going to need. We're going to need a triangle, pi on 3 triangle, so we can recall the side lengths. It should be 1, square root of 3, and 2. So where 1 is my adjacent side, square root of 3 is my opposite side, and of course 2 is the hypotenuse, right? Okay, and by the way, this is in the first quadrant, so everything is positive, okay? So note that we are in quadrant 1, so x and y are positive, so I'll just denote that by this. X and y are both positive. So I don't need to worry about any of these being negative. Okay, here we go. Sine of pi on 3 is opposite over hypotenuse, square root of 3 over 2. Cosine of pi on 3 is adjacent over hypotenuse, so 1 over 2. And now I'm going to list every single trig function. Tangent of pi on 3 is supposed to be opposite over adjacent, so square root of 3 over 1, right, which is just square root of 3. Cosecant of pi on 3 is supposed to be, 1 over, well, hypotenuse, hypotenuse over adjacent. No, hang on. I'm having a brain fart. Cosecant is hypotenuse over opposite, which is the reciprocal, should be the reciprocal of sine, right? So really when you're dealing with cosecant, secant, and cotangent, you don't really have to think too hard, because if you've already got these three, all you have to do is take the reciprocal. So to get cosecant, I flip sine, so I'm getting 2 over square root of 3. 2 over square root of 3. To get secant, I flip cosine, so just 2, 2 over 1, which is just 2. And here to get cotangent, I flip tangent, so square root of 3 over 1, technically, right? So 1 over square root of 3 to flip it. And you can rationalize these if you want, but no need. No absolute need to. But if you wanted to, what would you get? Let's see. You would get, if you rationalize this, you would get 2 square root of 3 over 3. And if you rationalize this, you would get square root of 3 over 3. If you'd like to do that. It's not necessary, and like homework and exams will accept answers like this. Okay, now part B, which I'll switch to blue. T equals pi on 2. Now this is less about the triangle, right? Because t equals pi on 2, we don't really draw a triangle for that kind of angle, right? This is on the x-axis, the positive y-axis. This is at 0, 1. So x is 0 and y is 1. So this is not really, when you get an angle that's on an axis, or this axis, then you don't really, it's not about drawing the reference triangle. It's about knowing where the coordinate point is on that particular axis. And for pi on 2, that puts us on the positive y-axis as 0, 1. So for sine, I know that my sine value should be directly equal to the y value. So sine of pi on 2 is 1. Cosine of pi on 2 should be straight up equal to the x value, 0. Tangent of pi on 2 should be y over x. Y over x, right? Y over x is going to be 1 over 0, so that's undefined. See that? 1 over x, right? Rather 1 over 0, y over x. Okay, now cosecant pi on 2 should be the reciprocal of sine. So instead of 1 over 1, it's going to be 1 over 1. Okay, it's just 1, right? It's just 1. Because cosecant should be 1 over y, but the y value is just 1, so it's 1 over 1. Okay. Secant should be 1 over x, the reciprocal, but you can't take the reciprocal of 0, right? That's undefined. Any of these that have an x in the denominator here at this particular angle, pi on 2, are going to be undefined because you can't have a 0 in the denominator. Finally, cotangent of pi on 2 is supposed to be x over y. That's okay. X over y is 0 over 1 here. That's 0. All of that is coming straight from these. Tangent t is y over x, etc. Okay. Give me 1 second to get organized. Oh, there's a table in section 6.2 that's going to give you all of these values, these trig function values for t equals 0, pi on 6, pi on 4, pi on 3, and pi on 2. For all 6 of them, it would be a really good exercise for you to go through and find all of them. In fact, I think the homework makes you do a couple of them. So it's called, where is it? Page. T equals 0, pi on 6, pi on 4, pi on 3, and pi on 2 for the 6 trig functions. Now remember, when you're asked to find terminal point, that's only dealing with sine and cosine. We're just expanding, in this section, we're expanding beyond that into the other 6 trig functions because we can talk about that now. Okay. Okay. Let's go back and talk about those domain issues now. So what about domain issues for, let's see, what should we start with? Cotangent and cosecant. They cannot have well, they have a y in the denominator, right? So they cannot have any t value that gives y equals 0. What t values give y equals 0? What angles or arc lengths give, why am I saying angles or arc lengths? Because on the unit circle, they're the same thing. Anyways, okay, so what t value gives a terminal point where y is 0? Well, that's either going to be here at 1, 0, or all the way over here. So by the way, what is this? This is t equals 0. And then or all the way over here at -1, 0, right? On the x-axis, that's where it's going to happen, here or here. Oof. Or any other combination. Any rotation that that ends up at either here or here is going to be not allowed in the domain for cotangent and cosecant. So how do we notate that? So we see that t cannot be 0, cannot be, that's that one. This one is pi, right? This is t equals pi over here for a half a revolution. T equals pi. And then, so 0, pi. What if I go all the way around? That's 2 pi. What if I go around half again? That's 3 pi, 4 pi, etc., right, etc. You get it. So how do I say this? So how do I say this? I say that t cannot be, well, here's an easier way to list all of these. T cannot be n pi, where n is any integer. Remember, the symbol for integers is just this like weird capital looking Z letter. Integers, wow, what am I? anyways, integers are the positive whole numbers and negative whole numbers and 0. So this is the way to sum up the domain issues for cotangent and cosecant. Now, what about tangent and secant? Because those also had domain issues. X cannot be 0. X equals 0 gives a domain issue because they have x's in the denominator. So what value of t lands us at x equals 0? Well, that's going to be values that land us on the y-axis. So an angle here, which is pi on 2, or an angle all the way down here, which is 3 pi on 2, because that's going to be corresponding to the point 0, 1, where x is 0, or the point 0, -1, where x is 0. And then any value that lands at those. So we can say just t cannot be pi on 2, 3 pi on 2, and all those odd half angles. So 5 pi on 2, 7 pi on 2, etc. How do we list that? Like in a nice compact way, like I did up here. T cannot be pi on 2 plus and then half revolutions. So we just kind of skew it. We start halfway and then we just start doing half revolutions just like we did back here. And again, where n is just an integer. Where n is just an integer. Okay. So for cosecant and cotangent, domain t values cannot be any n pi values. And for tangent and secant, it's half pi values that you need to worry about. Okay, that'll come up when we talk about their graphs. We'll see they have asymptotes there. Okay, we already talked about the sign. Let me say some more about the signs of the trig functions. Notes about signs of trig functions in each quadrant. So tangent, let's see, well, we already know about sine and cosine, right? Sine is positive where y is positive, and cosine is positive where x is positive. Tangent of t is positive where, well, it's y over x, right? So it's going to be positive where y and x are the same sign. In other words, quadrants 1 and quadrants 3. This applies to cotangent as well, so I'll say cotangent of t here. And then secant of t is the reciprocal of cosine, right? So it's going to be positive wherever cosine was positive, where x is positive. That's quadrants 1 and quadrants 4 on the right side. And cosecant of t is positive where y is positive. And that's going to be in the top. So quadrant 1 and quadrant 2. Okay. Okay. Some practice with the signs. Example 2 now. Cosine of 2 pi on 3. Well, since 2 pi on 3 is in quadrant 2, And cosine is only going to be positive where x is positive. So cosine of 2 pi on 3 is negative. Because x is negative in quadrant 2. So cosine of 2 pi on 3 is negative in quadrant 2. How about secant of 11 pi over 6? Well, 11 pi over 6 is in quadrant, where is that? That's almost a full revolution, right? 12 pi on 6 would be a full revolution, so this is in quadrant 4. So secant of 11 pi, well, secant is supposed to be positive wherever x is positive. It's the reciprocal of cosine, so its signs behave the same way as cosine. 11 pi on 6 is in quadrant 4. X is positive there. So that means secant in the fourth quadrant is positive, greater than 0, positive. Okay. (6.2). All right, let me take a look at my notes and see what else I've got. We still have some things to talk about first. 6.2, even odd properties. In fact, I'm just going to go ahead and get that out of the way now so we can start 6.3 on Wednesday, or I mean Monday. All right. Okay. Let's talk about some even odd properties. So recall from MS 112 that f of x is even as a function. Even odd, even or odd is I'm talking about a property of a function. F of x is even if you give it a negative value and it just absorbs that negative and just says nope, no change. It just absorbs the negative. F of x is odd if f of negative x, you can pull the negative on the outside. So just a real quick example, like f of x equals x to the fourth plus 2x squared. If I plug in f of negative x, I get negative x to the fourth plus 2 negative x squared, which is just that's going to absorb that negative. That's that even both of the even exponents absorb the negatives, and that's kind of what you discovered in 112 is that if all the exponents are even, then your function is even, and likewise if all your exponents are odd, then your function is odd. So what about trig functions? Well, let me finish this example first. So here I'm getting negative x cubed is just the same as, well, negative x times negative x times negative x is x cubed, but negative, and then minus x, right? So they both change signs, so it's negative of x cubed plus x, which is exactly the definition of an odd function. So here's an even, and here's an even, and here's an odd function. Now, what about the trig functions? What about the trig functions? Well, without getting into too much details, let's just say sine of negative t is equal to negative sine of t. So sine is odd. Likewise, cosecant of negative t is equal to negative. So that kind of makes sense since these are reciprocals of each other. Tangent of negative t is also going to be odd. So these are nice properties to keep in mind. If you've got negatives inside of these three functions, or actually the cotangent as well, if you've got negatives inside, you can just pull them outside. That's pretty nice. That's a good property. These are all odd. And then you've got cosine of negative t is equal. So cosine is even. It just absorbs negatives. And secant of negative t is also even. Secant is also even. It absorbs negatives as well. And this is just inherent in the way that the fact that cosine and secant are both dependent on x. And we could go into details about this, but for now I just want to say, just note these properties. Recalling even and odd from 112 and noting that our 6 trig functions do have these nice properties. In fact, they all have one or the other, with cosine and secant being even and the rest being odd. So that means if we wanted to do something like cosine, if I said find cosine of negative pi on 4, you could just say, well, that goes this way, but wait, I don't need to do that because I can just say that's the same as cosine of pi on 4. And I know that is just square root of 2 over 2. So I don't need to worry about the negative. Or if I said, what's sine of negative pi on 6? You could say, okay, so that angle goes clockwise, or wait, no, I can just pull the negative outside. Sine of pi on 6 is 1/2. Yeah, sine of pi on 6 is 1/2, so negative sine of pi on 6 is negative 1/2. So that's how these properties can be pretty useful, saving you some work dealing with negative, trying to not have to deal with negative angles. Okay, a couple more properties coming here. Let's talk about some Pythagorean identities. Note that for the unit circle, which is where we are living for this chapter, x squared plus y squared is equal to 1, but also x is equal to cosine of t and y is equal to sine of t. Put these together, what do I get? I get cosine squared of t, that's x squared, plus sine squared of t, that's equal to 1. This is called the Pythagorean identity. Or rather, it's one of them, but it's kind of the most popular one. So just keep this in mind. Keep this in mind. There are other versions of it. Which we'll talk more about whenever we talk about identities, which I think that comes in chapter 7. Yep. But there are other versions of it. I'll go ahead and write them down now. That tangent squared of t plus 1 is going to be, let's see, divided by sine cosecant. No. Hang on. Sorry, secant. I mixed myself up. Secant squared of t. And then there's another one that is 1 plus cotangent squared of t is equal to cosecant squared of t. These are together called the Pythagorean identities. This one really is the most useful, the first one, coming straight from the fact that we're on the unit circle and x is equal to cosine t and y is equal to sine t. Very, very useful. These other ones, if you're going on to calculus, these will be useful in some weird calculus problems that you have to do. And we'll use them too, but really it's that one right there is the real important one. All right. That's it for 6.1. 6.2. Some problems to mark for review. I will send these to you later because I want to go look at the exam again and before I pick the problems. So these will be coming via email. All right, that's it for 6.2.